Hello, everybody. So in this video, I'll be covering Diels-Alder reaction. Now, before we proceed on to do questions with Diels-Alder, what I want to do is go over the concept. How do you approach the Diels-Alder reaction, going forwards, going backwards, understanding how an intermolecular Diels-Alder reaction works. All right, guys, so let's get started. Now, before we do anything, here's this beautiful template. And what I like about this template, it helps you understand how to do it step by step. So for a Diels-Alder reaction, you're always creating a 6-membered ring. The diene is always going to have 2 double bonds. And for the majority of the time, it's always going to have your electron donating groups, like an OCH3 or a methyl. Those are just 2 examples. It can be anything else that's an electron donating group. For the EWG, the electron withdrawing groups, they're always going to be electronegative atoms, like a ketone, like a double bonded O. You can have an ester, or you can have a cyano group. Those are like 3 main ones you'll probably see in organic chemistry. There's more to it, but for the most part, those are the majority ones you'll kind of see in a way. But that's just the identification that you're doing a dienophile, and it's always going to have 1 double bond. Okay. Now, what I like to do first is I like to start with my diene, and I like to number it 1 through 4. Then I'd mark my dienophile. You're always going to have 3 arrows floating into space. You're always going to have a double bond between carbons 2 and 3. Number 4 will connect to number 5, and then number 6 will connect to number 1. So I'm going to draw a 6-membered ring. I'm going to number it 1 through 6. 1, 2, 3, 4, 5, 6. I'm placing a double bond between carbons 2 and 3. And then after that, all you have to do now is just match up the stereochemistry. So like if you look at number 1, our T is pointing outwards, so is number 4. They're going to have the same stereochemistry. Same thing goes for the C's inwards. They're going to have the same stereochemistry. For X and Y, they're also going to have the same stereochemistry. They're pointing in the same direction. Same thing for EWG and Z. Same stereochemistry. And since you can't determine the stereochemistry, you can also get the intermit where you change every one of them. So that's usually how you make a Diels-Alder reaction. Okay, so now we're going to use this template, and this template is going to help us out with the other questions. Now, with understanding Diels-Alder reaction, you have to understand regioselectivity. Now, regioselectivity is so important. And what indicates this, if you have an electron donating group, you have to understand electron donating groups are always going to have the partial positive charges. Electron withdrawing groups are always going to have the partial negative charge. And in order to do this, we must show residence. So I gave myself a head start. I redrew this product of the diene, and I showed that we have an electron donating group, very strong electron donating group, where it's able to donate electrons and show you that it's going to have that partial positive charge, and that the last carbon is going to have that partial negative charge. Now we do the EWG, the dienophile, with the electron withdrawing group. And since we know this is electronegative, this double bond is going to shift over here so that oxygen can attain that minus charge. And just by looking at the charges, partial positive matching of a partial negative matching of a partial positive. So by doing regioselectivity, double checking your work, we did this 100% correct. And now we're able to proceed on with the Diels-Alder reaction. So I'm going back to the top. I'm going to draw my 3 arrows floating into space. We're always going to have a double bond between carbons 2 and 3. 4 will connect to 5, and 6 will connect to 1. So we're going to draw a 6-membered ring. We're going to number it 1 through 6. Double bond on 2 and 3. OCH3 is pointing outwards. It's facing the T position. So we're going to make it a wedge.